Hi everyone, I am Salman. I am a PhD student at Inha University in South Korea. This work is supported by my academic advisor, Professor Noh at Kentucky University, and co-advisor, Professor Lee at KAIST University in South Korea. My talk is related to spy camera detection. The question is why the spy camera is a high privacy concern. I would like to answer this from three aspects. First, it is installed in a private zone. Here are a couple of examples of spy camera detection in Airbnb, hotels, restroom, and fitting rooms reported by various surveys and the news channels. The US finance company shows that around 11% of the candidates stayed in the Airbnb have found the spy camera there. And other news reported that the spy camera spotted in Korea at various hotels, filming around 1,600 guests. Similarly, there are a couple of reports where the spy camera has been found in restroom and fitting rooms of the shopping malls. Secondly, the spy camera is very tiny and it has the Wi-Fi support. The tiny size enables its unsuspected packaging. For example, its packaging in power socket, charger, and clocks, etc. Whilst the Wi-Fi support enables its placing in any unexpected locations. Owing to these features, it can easily record the individual private zone without their consents. Lastly, spy camera has severe impact in our daily life because its contents could be made available over the internet, which also results in increasing the voyeurism crime. Furthermore, the recorded contents could also be used for blackmailing purpose. It is heartbreaking that several victims, including celebrities, committed suicide because of losing their self-esteem due to unwanted exposure. Because of these high privacy concerns, there are a couple of solutions available in the form of hardware and software. Some of the examples of hardware-based solution are shown in the left side. DeSpy RF detector is designed to detect any RF signal on the ISM license-free band. However, this solution is not reliable because many other RF devices could also use the ISM band. The Spy Camera Hunter detects and displays the video streaming by the analog video sources such as PAL, NTSC, and SECAM. Unfortunately, the modern spy camera do not use them. The software-based solution includes finding a camera by inspecting its traffic. The first one work is correlating the timing pattern of a known camera with that of a suspicious streaming. This work, however, does not consider various parameters that can mislead the camera detection. For instance, resolution difference, codec difference, variation in the complex scene observed from a different angle, etc. The other work are related to the direction of a bitrate on the light stimulus from a dedicated hardware. However, the bitrate can easily be affected by the recurrent high-sized frame transmission due to the underlying compression algorithm and the jitter caused by the network. Finally, the DV-cam correlates the variation of accelerometer reading and the bitrate of a person aggressively moving in the recorded zone. Such system requires laborious activity, pre-planned action, and carrying the smartphone. So how to protect the privacy and vision with affordable solution? It is highly desirable that we have a system that should be reliable, which means it should not require any labor-intensive efforts or should not use any hardware for stimulus and should work in any kind of environment. It should be practicable, which means it should not require any pre-planned actions, and it should be unobtrusive, which means the user should not require to carry the smartphone for the camera detection. The functionality of CSI DeSpy on a high level is shown in this figure. The data packets conveys the recorded information of a target scene, whereas the channel state information or the CSI conveys the activity information of the target individual. Intuitively, both words carries the same information. If the target person moves in the target scene, the compression algorithm will transmit high data rates due to the variation in the group of pictures. Furthermore, when the physical layer RF signal strikes the body of a target individual, they also show variations. When these quantities show similar information at common timestamps, it will predict the camera availability. You can clearly see no activity for initial 10 seconds and then an activity for the following 20 seconds. The CSI adaptation, however, introduces some inherent challenges. The first one is the effect of multipath. As you can see in the picture, the signal received at the receiver arrives from multipath reflections, which aids constructively or destructively, thereby causing degradation to the received signal. In this figure, the reflections are not always from the target individual, denoted by the blue line, but also from other static objects. The CSI DeSpy should be able to effectively capture the reflection from the target individual and discard the irrelevant multipaths. The sensitivity of CSI DeSpy depends on diverse physical activities and different indoor environmental conditions, where the multipath effect depends on the scatters in that area and the interval distances. For instance, the person might be doing a mild or vigorous physical activity. Also, the person might be in small room or a big room. And any type of condition, the CSI DeSpy should be able to work. And the user should not be obligated to perform some pre-planned activities, such as staying still for initial 15 seconds and then move for the rest of the time. This would cause significant amount of discomfort to the user. The CSI DeSpy should be working with activity of daily living with no preset conditions. And finally, the user should not carry the CSI DeSpy enabled smartphone for the camera detection, whereas the smartphone could be placed in any part of the room and the camera should still be detected. This figure shows the big picture of our methodology. The person can do any activity of daily living. This activity is taken as an input by the auto-tuned DB-scan method. To adapt the CSI DeSpy to the variation of activity intensity and multipath environment, it performs 3 steps. First, it estimates the input parameters automatically. Then it tunes the parameters further to effectively detect the state of activity. And finally, it detects the static state of the target individual and derive a control limit threshold for the control chart method. We leverage this statistical process control method to classify the static and dynamic states of the activity of the individual in real time. When the activities from the bitrate and the CSI at common timestamps are correlated, then the camera availability is anticipated. The default DB scan method has one potential drawback, and that is the manual adjustment of the input parameters, namely epsilon, which is the radius of the core data point, and minimum points, which must be there in a data point in order to be a core point. As shown in these two examples, epsilon is different from the data taken for different rooms. This is due to the multipath effect. Therefore, a fixed epsilon and minimum point could not effectively classify the cluster belonging to the static and dynamic data points. For this reason, we estimate these values automatically by leveraging the following methods. First, the sorted data point is flipped by 180 degrees about the origin by the line formed by the endpoints. This transforms it into negative concavity. The purpose of the line between the endpoint is to preserve the overall behavior of the dataset. Moreover, in order to maintain the original trend or shape, the data points on both axes have been normalized. The curve shown in the above figure is rotated by some degrees clockwise about the origin until the line formed by the endpoints overlaps the x-axis as shown in this second figure. Since the data points have been sorted in increasing order, therefore, there is always a single global maxima. The knee point determined with this procedure lies in between the value which are slowly changing, or we are also calling it consistent core data points, and the values which are drastically changing, which are the dispersed core points or outliers. Intuitively, this is the bifurcation point and dataset that separate the two clusters, for example, static and dynamic clusters. Finally, this data point is translated to the sorted data points as shown in figure 3. It is possible that the instance of one activity is shorter than the other activity. Sometimes the shorter activity state is masked by the longer activity, and we get a single cluster regardless of two different activities. This can be corrected with auto-tuning method, which gradually reduce the epsilon value whilst increasing the minimum points in the core point. Finally, we get a tune parameter where the cluster belonging to different states are separated. To evaluate our system, we conducted activities of different stimulus. For example, light physical activity, where we were changing the jackets, the moderate activity, where we were walking in the room at moderate speed of 1.5 meter per second, and vigorous activity, where we were doing 3 skips per second in front of the camera. In addition to that, we considered 3 rooms of different sizes, namely small room, medium room, and large room with uncontrolled furniture arrangement as shown in this figure. For the sake of brevity, we would just explain the worst case scenario here with all the physical activity in the small room where the multipath is severe due to less interval distance. We can see that the plane control chart method is based on a non-adaptive and hard-coded threshold. Therefore, its detection rate is poor and has a higher false alarm rate. On the contrary, the self-adaptive method outperforms the control chart cases. We receive over 95% of detection rate and less than 6% of false alarm rate for all the self-adaptive cases. The human activity of daily living are unpredictable in nature. To mimic this, we remain static for as less as 2 seconds in scenario 1, 4 seconds in scenario 2, 6 seconds in scenario 6, and for entire 8 seconds in scenario 4. We have different and random instances of static and dynamic interval when we are doing some activity of daily living. For example, when changing clothes, we remain static for shorter interval for opening or closing the buttons or zip. However, for the rest of the interval, we are moving. For pressing clothes, we might have equal chances of staying static and dynamic. We can accurately capture all these activity with our self-adaptive DB scan method. And this is the result for all the above four cases. Here, it is noteworthy that the more we remain static, the higher will be the accuracy, because the static cluster can accurately adapt to the threshold for the control chart method. Finally, to assess the unobtrusiveness of our system, we place CSI DeSpy-enabled smartphone at different locations of the room as shown in this figure. In addition, we also added some noise from the person in non-line of sight who was consistently walking outside the room. We saw that with anywhere placement of the smartphone, our detection rate was above 95% and false alarm rate was less than 3%. To conclude this, we devised a solution for detecting a spy camera by leveraging the channel state information and payload distribution of the spy camera, which is monitoring the private zone. Our camera detector is reliable, which means it does not require laborious activity and works in diverse, uncontrolled indoor environments. It is practicable, which means working with activity of daily living. Unobtrusive, thanks to its passive sensing feature, and does not require any external hardware. Thank you for having your attention.